Good afternoon.
Good afternoon.
Was like about me.
Good afternoon, Professor.
Good afternoon.
Childization. Convene carry.
Hey guys, welcome back to the course, day 9, I think, of 28. The first item for business, of business. I talked to Tariq, the TA, one of the TA, the lab TA. He told me that 28 of you have sent him your info as to shipping. That means 6 of you have yet to do so, if my arithmetic is correct. So I'm asking for those 6 names, and I'm going to contact those 6, or he's going to contact those personally. It's really important at this point to provide the TAs with your shipping information, because without that, you won't be able to do the lab. And so you either have to let us know whether you will come to Steinman, and if not, then where we can send the kids. And so that this is super important. So if you're one of those 6 students that has not provided the info, please do so immediately. If you're picking up on campus, you're good. It's only if you're not. So basically, if you haven't sent Tariq an email about picking up the circuit kits, you got to do so like now. All right. Okay, Eric, go ahead with your question about number 6, and feel free to share your screen so that you can point me to the confusion.
Okay, so with question 6, I don't know how to share my screen.
Sure.
For nodes RAB, are the 2.7 kilo ohms and the 2.5 kilo ohms resistors part of that part of the question?
Sorry, are you able to share your, I don't see the, can you, could you share your screen and then point to exactly what you're asking about?
So these 2 resistors right here, are they part of the overall RAB node?
Well, so that's see, this is one of those questions that I shouldn't really answer, because that's part of the that's part of the question, right? Mm-hmm. So let me ask you, remember what I said about nodes and circuits, where if you can trace a line from one point to another without passing through a resistor or another element, then it's the same node, right? And so node B, right?
Okay.
So go left and go down. Now, yeah, you're still at node B.
Okay, so if I go left again.
Right, so you're still at node B. So do you understand what I'm saying?
Yes, I got it.
Okay, so does that clear up your confusion?
Yes.
Okay, good.
Right. Thank you.
No problem.
Now I'm confused.
Okay, go ahead.
I just don't. Okay, I'm gonna share my screen. Just 1 second.
Sure.
Professor, can I clarify whether
Go ahead.
would it be that since if a current would flow from those two ends to node B, we can conclude that both the series and the parallel contribute to the resistance, to the voltage, to the resistance B. I don't know if that makes sense the way I'm saying it.
Potentially, I mean, you can't, like, that whole picture there is one circuit. And so you can
Yeah,
probe
yes.
that circuit in different nodes. But in potentially every node is sensitive to every other spot on the circuit. So, you know, node B can react to something way down at the bottom of the circuit. You know, it's not, whenever you're solving a circuit, don't assume that you can just exclude something unless you have a very compelling reason to do so. Like maybe if something is being shorted, or if something is being open circuited, then maybe. But you know, what you should be answering in this question is to go from point A to point B. How much resistance do you encounter? Right? And then you have to trace all the possible paths to get from A to B and count up the
Exactly, so you would
resistance.
follow the current, the potential current that would flow from point A to point B.
Yeah, you don't have to worry about anything current or voltage related here. The only thing you have to worry about is which and remember, from point A to point B, for example, which resistors are in series and which resistors are in parallel. That's all you need to do. And then you have to apply the laws of resistor combination to figure out the equivalent resistance between A and B. Right. So I mean, so I'm gonna the student that said they were confused. Do you want to?
So yeah, so basically, like, it doesn't matter the path as long as you get there. So like you can go like that, you can go like that, you can go like that. So like these three paths, all of them count into the RAB.
They all count, but they all count. You know, to get the actual value for the resistance, you have to. You know, for example, you have to consider things like every path from A to B will traverse the parallel combination of the 235 and the 1.8 kilo, right? There's no way of getting from A to B without going through one of those.
Yes.
Agree?
Agreed.
So then those two are what those two resistors are, how are they connected to each other?
They are in parallel, so we add them.
Exactly. So they're in parallel. So to make your life easier, you should just redraw the circuit with those two combined into a single resistor.
I did that part, but my confusion part with the 2.7 and the 2.5, I didn't, like, for example, I didn't include them because I felt that from A to B, you're just gonna go from, like, you have to add these, and then I added these, for example, and you can like go like that, and then when these are added, you just can go like that.
Why would the current not choose to go through the 2.7 and 2.5?
Higher resistance.
Right. I'll grant you that it's higher, but it doesn't mean that there's nothing there, right? It's still gonna, like, I'm already giving away the answer, which I shouldn't. What if I had just changed the order of those three branches, right? The 1.2 to 500 and the 2.7, 2.5. What if I had drawn the 2.7 and the 2.5 above? Would you still ignore them?
Probably not, but no. If I use
Right.
the concept that like higher resistance means less current, and the current is going to choose the least resistive path, then I will choose the least resistive path.
Yeah, but there's still the 2.7 and the 2.5 are still going to have an influence
Okay.
on if you just look at the node right before the 1.2 kilo ohm resistor. Yeah, anywhere there, yeah, right, that node. To go from there to point B, you have 3 different ways, and all 3 need to be accounted for.
Okay.
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 So yeah, you do need to account for all possible paths.
Okay. Thank you, Professor.
No problem. Is there any other questions about the homework? All righty. There's a potential for this lecture being fairly short, so it's good news. We are on Norton's theorem, and the other good news is that Norton's theorem is very similar to Thevenin. So, okay. So first of all, as a recap of last class, Thevenin's theorem states that any linear circuit can be replaced with a simpler circuit that consists of a battery in series with a resistor. And to figure out the value of that battery and the value of that resistor, we do 2 things. One, we disconnect the independent sources in the original circuit, and we look at how much impedance that circuit poses when looking at the 2 terminals that you're interested in. And step 2 is to solve for the open circuit voltage at those 2 terminals with everything on. Give me 1 second here. And so Norton's theorem is very similar. Basically, the only difference is that instead of replacing the circuit with a battery in series with a resistor, you replace it with a current source in parallel with a resistor. Okay, so any linear 2-terminal circuit can be replaced by an equivalent circuit consisting of a current source in parallel with a resistor. Now here's another important difference. The value of that current source is no longer going to be equal to the open circuit voltage. Instead, it's going to be equal to the short circuit current. Rn is the same. So let me just explain what the term short circuit current means. It's not a difficult concept. So you have your original circuit. It has 2 terminals. You're looking at this circuit from the point of view of A and B. And so what you're going to do is replace that generic circuit with a current source in parallel with the Norton resistance. And to figure out the value of IN, you're going to connect A and B, and you're going to measure how much current flows there. Okay, so Rn is found the same way as RTH. So you disconnect your independent sources. So going back to this slide, you will disconnect all independent sources in the original circuit, and you'll figure out the equivalent impedance as viewed from terminals A and B, just the same as last class. The difference is how you compute the Norton current. Okay, so what you do here is you short circuit A and B. Now what that means is you just connect them with no resistance. And then you see how much current ends up flowing through your short circuit. And then another nice property is that the Norton current is always going to be equal to the Thevenin voltage divided by the Thevenin resistance. which means that, you know, there are three quantities of a circuit, of a linear circuit. You have the Thevenin voltage, the Norton current, and the equivalent resistance. And if you have two of them, you can get the third just by using Ohm's law. And so these two techniques, Thevenin equivalent and Norton equivalent, they really are two sides of the same coin. You're basically performing the same operation due to Ohm's law. And so, as in Thevenin analysis, if you have dependent sources in your original circuit, when you're solving for IN, you will keep those in. You will not disconnect the dependent sources. Remember, a dependent source responds to other other branches of the circuit, so you cannot disconnect it. Okay, so we need two of three quantities. We either need to reduce a circuit to its Thevenin or Norton equivalent. We either get the open circuit voltage, so in other words, you leave A and B unconnected and you figure out what the voltage is across them, or you connect them with a short and you figure out how much current that short is carrying. And three, you turn off your independent sources and then you measure how much input resistance the circuit presents when looking from terminals A and B. So here are the three quantities expressed. You know, the Thevenin voltage is just the open circuit voltage. So OC stands for open circuit. The Norton current is the short circuit current. SC stands for short circuit. And the Thevenin resistance is equal to the Norton resistance. And those are equal to the Thevenin voltage divided by the Norton current. In other words, if, for example, you didn't feel like computing the equivalent impedance, you could just solve for the Thevenin voltage and then solve for the Norton current and then use Ohm's law. It's up to you which two of these three you solve for, but usually you solve for VTH and RTH, or you solve for IN and RN. Okay, so let's do our first Norton example. So here we have a fairly simple circuit that has two independent sources. We have a 2 amp current source on the left and a 12-volt battery connected in series with a 4 ohm resistor. Then we have a network of 3 resistors. Our terminals are here on the right. So the first step is to find RN, right? So we disconnect the 2 amp source, and that's why this branch now is open, and we short circuit the battery. So remember, 0 amps means open circuit, 0 volts means short circuit. So here we are back to, you know, the problem of reducing resistors, right? So here's an example of what we were just talking about with respect to the homework. To go from point A to point B, how many possible paths are there? Well, there are 2. One path is just a direct one across the 5 ohm resistor. And the second path is to take the long way, going through the 8, then the 4, and then the 8. So we have a 20 ohm path here and a 5 ohm path here. And those two are in parallel because this is the top node and this is the bottom node. Right, so we have a 5 in parallel with a 20. So notice that the result of combining a 5 ohm resistor in parallel with a 20 is equal to 4. So the answer is always going to be less than the smaller of the two numbers. many of you have probably already observed that the parallel combination is always less than the smaller of the two numbers, right? Because the kind of the intuition behind that is that if you present a current with more than one path, then it effectively has to have less resistance than any one individual path. Okay, so that's the solution for Rn. Rn is equal to 4 ohms, so we're halfway there. The second step now is to short circuit A and B and figure out how much current is going to flow between A and B. Okay, so we short circuit A and B. And so here we're going to apply mesh analysis. So what I would like to ask you guys is, why is this mesh current symbol drawn over here? And why do we not have I1, I2, and I3? Okay, we have an answer on the chat, 2 answers on the chat.
It's because we short circuited, so all the current's gonna go through A and B and not take the resistor because there's no resistance on that path.
Yeah, exactly. So I think yours and Sergio's answer are the same. So namely, this 5 ohm resistor does not come into play anymore because it's in parallel with a short, right? So this 5 ohm resistor is connecting A and B, but A and B are connected by a 0 impedance connection. And so this branch will not draw any current. The current will bypass the 5 ohm resistor and go directly from A to B. And so what you effectively have is a 2 mesh circuit over here where I1 is given to us by 2. And then the second mesh is the outside one, right? You can just ignore this branch here for the sake of determining IN. And this will happen a lot when you're doing Norton, because when you do Norton, you short circuit A and B. So anything that's in parallel with that will be ignored. Okay, let's see. Our KVL equation for this mesh here, we have -12 plus 4I2 minus I1 plus 8I2 is equal to 0. And that, plus, yeah. So again, we have 4 plus 8 plus 8, that's 20 ohms along mesh 2. And 4 of those ohms are common to mesh 1. And then we have a voltage rise of 12 volts, which is indicated with a -12 on the left side. So now we have everything we need. I2 is equal to 1 amp, which is equal to the Norton current. And so we could have also determined IN by solving for the Thevenin voltage. And so, for example, we could have left A and B open circuited and done another mesh analysis problem, but this time with I3 over here and I4 over here. So again, I3 is still equal to 2 amps. But now the KVL equation for this mesh will look different because the 5 ohm resistor in this configuration is not shorted, right? Because now there's no more short circuit between A and B. And when you do this analysis, you figure out that VOC, which is the voltage between A and B, which is also the voltage across the 5 ohm resistor, is equal to 4 volts. And if you remember from the previous slide, that our Norton resistance was 4 ohms. And so we know that the Norton current is equal to the Thevenin voltage divided by the equivalent impedance, which gives us 4 divided by 4, which is 1 amp. So you do not have to do this step. This step is just demonstrated to show you that to find the Norton current, the first way is to short circuit A and B and figure out how much current flows here. The second step is to leave A and B open, solve for that open circuit voltage, and use Ohm's law to find the value of IN. Okay, so I'm just going to pause here for a second, and if there's anybody that has questions about this problem, please let me know.
Professor, are we ignoring the 5 ohm resistor?
In panel B, yes, not in panel C. And the reason that we can ignore it in panel B is because it's in parallel with a short.
Professor, can you go back one slide?
Mm-hmm. Sure.
So when you did the Norton equivalent, I was just confused. Why did you separate the 5 ohm from the rest, and what did the 2 bars represent?
Oh, the 2 bars mean in parallel.
Okay.
And the reason that I separated the 5 ohm from the other 3 is because remember, to get from point A to point B,
Yeah.
in this network, there are 2 paths. The first path is to take the 5 ohm resistance, and the second path is to take the 8, then the 4, and then the 8.
Ooh, so we just do it by paths.
Yeah, and I mean, another way of saying is that the 5 is in parallel to the series combination of 8, 4, and 8.
Would we ever have more than 2 paths?
Oh yeah, I mean, there's, many multiples. I mean, another way of doing it is just the 8, the 4, and the 8 are all in, I mean, if you want to do it sequentially, then the 8 is in series with the 4. So you could replace those with a 12.
So you could do 12 bar 13?
No, because the 5 is not in series with the 12 and the 8. So if I let me draw.
No, I'm saying then it could be you combine the 8 and 4, and then you put that in as parallel to the 5 and 8. That's what I was
Yeah,
saying.
but I'm gonna do it for you. I'm gonna show you that it's still not.
Doesn't work.
No, I'll show you. So this is the 12 here that you're talking about. This is the 8.
Yeah.
And this is the 5, right? The problem with combining them all is you are measuring the resistance between this point and this point, right? To go from here to here, you can still go only through the 5. And so it's still 20. So this, let me just use a different color here. You can, the 2 nodes, this is node A and this is node B. Okay, so to get from node A to node B, there's two paths, right? So the 5 ohm resistor, this is the top node and this is its bottom node. The 12 and the 8, so I would actually combine the 12 and 8 once more into a 20, but I'm not going to draw it for the sake of time. So then you would basically, actually, let me just draw it because I think, I don't know, it may help people, and it really is so you could, again, combine the 12 and the 8. This will be 20. And this will be 5. And these are your 2 terminals. Okay. And so here it's clear that the 20 and the 5 are in parallel and they're not in series.
Mhm.
Does that make sense?
Yes.
Okay, good.
And then just one other, the 5 ohms that the 5 ohms, is it
Yeah.
like in the original, I guess, circuit question that it's, presented when you see it the first time, is it already short circuited or do we do that part ourselves?
It's not short circuited in a circuit. It becomes short circuited when it's time to solve for the Norton current.
Okay. Yeah, okay, good. Well, that's what I was asking too. But thank you.
You're
That
welcome.
one. Do we have to remove the 12 volts and the 2 amps, or is that just to like make it easier so that we don't see any other obstructions?
You have to for the when you find to solve for the Norton current, you have to disconnect. Oh, sorry. What am I saying? You disconnect and to find the impedance. Oh, but what you're the only if you don't want to disconnect them. Sorry, I've lost my cursor. Give me just 1 second. You disconnect them when you how do I do this again? Oh, that didn't work. Okay.
To find the Norton resistance.
Yeah, to find the Norton resistance. Another way of doing it would be, let me see if I can end the slideshow and then I can do more drawing. Okay, so if for the easiest way, especially in a circuit that doesn't have any dependent sources, is to turn them off and measure the impedance looking from terminals A and B. If you didn't want to, if you could keep them in, but then you would have to apply a like a test voltage over here of, you would have to apply a test voltage of 1 volt. And then you could measure how much current I naught flows in. When you apply 1 volt battery, how much current flows into the circuit. And then you could say that Rn is equal to 1 volt over by I naught. Okay, so, but I want to recommend doing this. You have to do it if there's a dependent source. But if there isn't, it's easiest. You always have to disconnect the independent sources basically, unless you're comfortable with pain.
You mean like you just won't be able to solve it?
No, you'll be able to solve it. It's just here to solve this circuit, you'll have to do a 3-mesh analysis problem. Now you have 1 mesh, 2 mesh, 3 mesh. By disconnecting them, you just have 4 resistors. You just have to combine them and you're done.
So you can't just keep them in and assume there's no resistance going on in those components and just like visualize those 4 resistors.
That's right. You can't. Yeah, you have to.
Okay.
You either disconnect them. So by disconnecting, it means your current source becomes an open circuit and your voltage source becomes a short circuit. And then you add up the resistance. Otherwise, if you want to leave them in, you got to do this approach: a test voltage, and you see how much current flows in. All right, I have my cursor back. Let's go on. We did this one. We will move on to our first practice problem, which I'm hoping to get some help on from you guys. Find the Norton equivalent of this circuit. So we're going to short circuit the 15 volts, and we're going to open circuit the 4 amps. And so here is the circuit that remains, right? The 15 volts is now short circuited, and the 4 amps, which was here, is now gone. It's open circuited. So who can tell me the Rn between, as viewed from A and B, which are across the 6 ohm resistors? 3 is correct, Christian. It's 6 in parallel with 6, right? Because the 2 3s are in series, so they combine to a 6. And then the 6 in parallel with a 6 is 3. Okay. And so to find IN, we're going to short circuit A and B. Okay. So when you short circuit A and B, you get this equation. So now what happens to the 6 ohm resistor in this picture?
It gets bypassed.
That's right, it gets bypassed. So you can just ignore it. So we can just do a very simple nodal analysis with one node V. So what is the value of the current from here to here? From here, expressed in terms of voltages and resistors.
It should be 5 amps, right?
Nope, you don't know that yet, because this is not ground. It would be 5 amps only if V was equal to 0. So this current here is 15 minus V divided by 3. Yeah, Christian, that's right. Put the parentheses around the 15 minus V. How much current is flowing from here to here? Yes, very good. V over 3, excellent. Because this node, this is all ground over here, which means that A is also grounded, right? So the voltage here is 0, right? So we have V minus 15 over 3 plus V over 3 is equal to 4. So the 4 is flowing in. So I'm gonna do this because right, the 4 is flowing in. Actually, I did it backwards here. The way I did it was like this, right? So this current here is the 4, that's flowing in, and then flowing out is V minus 15 over 3, and this is V minus 0 over 3. Okay. And then there's no current through the 6 ohm resistor. So you can just solve this equation for V, you get 13.5 volts, which means that the Norton current, which is the current that flows from A to B, is equal to V over 3, which is 4.5 amps. Which means that our circuit, oh, we're done. I usually draw, but I forgot to draw what the final circuit looks like. So I'll just, which direction is the voltage flowing through the 3 ohm resistor? It's going from here to here, left to right. So the V minus 0 over 3. So remember, I drew, the arrows were drawn like this, and like this. All right, so the 4 amps is entering node V. You're welcome. And the V minus 15 over 3 is exiting, and V minus 0 over 3 is exiting. So our Norton current is 4.5, and our Norton resistance is 3. Moving right along.
So you could assume the bottom wires are ground 0 even if there's no ground symbol.
Yeah, that's a good question. So basically, yeah, I mean, we routinely just omit to draw it, but you can put the ground anywhere in the circuit. And most, if it's not labeled, you can just assume that it's at the bottom. But yeah, there has to be a reference, because voltage by itself is meaningless. You always need to have a point of a point of reference. Okay. So here we have a case where we have a dependent current source of 2ix. And this should be a lowercase ix. This ix and this ix are the same. So here is our first encounter with a circuit where finding the Norton equivalent requires one of these test voltages or test currents. So first of all, we're gonna disconnect the 10-volt battery. And we're going to, as a result, the 4 ohm disappears, right? Because the 4 ohm is now shorted by the disconnected battery. So all we have is the 2ix dependent source, the 5 ohm resistor, which is in parallel. And now we have a voltage source, a test voltage source that we put in. We can call it 1 volt. And our job is to determine the value of I naught here. So I would like you, because I really like this problem because it's simple, but it requires you to think. So I want you to apply KCL at this node over here. Who can help me apply KCL at this node where my cursor is or was? Bye-bye cursor.
So would it be 2ix plus ix plus I naught
Equals to what?
0?
Yes, that is good. I'm gonna have to again. Let's see, what's the way that I do that? I do that. Okay. But before that, we can actually, I should have asked you for the expression for ix first. So let's just go over this, and then I'm gonna try to get you to explain to me how I got this. So I have written down that ix is equal to -1 volt over 5 amps, which is minus 0.2 of an amp. So how did I get the 0 over here? That's my question. This point here is sitting at 1 volt, right? I think that's right. This is ground. This is 1 volt. This is 1 volt. But why is this node at 0?
It's the same node.
Exactly.
Same thing.
It's the same node as node B, right? This is ground. This is ground. So this is 0 volts minus 1 volt over 5. It gives you the current Ix. And then what you said, I think Omar, the KCL is 3Ix plus I0 equals to 0, which means that I0 is equal to 0.6 of an amp, right? Because we just substituted negative 0.2 for Ix in this KCL equation. All right. So let's see. So Rn, right, is by definition, Rn is equal to V naught divided by I naught. And V naught was specified by us to be 1 volt. And I naught, we just solved for, was 0.6. So 1 over 0.6 is 5/3. So our Norton resistance is 5 1/3 ohms. Okay, so we're halfway done with the Norton equivalent of this circuit. Sorry, Kuzema, that's just a typo. It actually comes from the book, but I could have fixed it easily. They're the same. There's no difference. So in this problem, Ix is equal to Ix. Sorry for the confusion. Okay, now we're going to find the short circuit current. So we're going to short circuit A and B, right? And that gives us this picture. And we have to figure out what the value of this IN is. So who can offer a suggestion for how we can compute the value of IN in this picture?
You can do 2 mesh analysis, one in that ignoring the 5 ohms, right? Can you? and then the other between the 4 ohms and 10
We
volts.
could, but I would argue that we don't need to resort to mesh analysis for this problem. What's the voltage at
Wouldn't
this
it-
point? What's the voltage at this point here?
10,
What's the voltage at this point here?
0.
0, which means that what is the value of Ix?
Over 5, right? 2.
Yeah.
2 amps.
It's 10 over 5. So 2 amps is flowing here, which means how much is flowing here?
4.
4, right?
Oh,
So the total, oh my God, I just contradicted myself. I can't believe I did. I don't even remember my own solutions. But there, 2 plus 4 equals 6. So your original suggestion was exactly what was in the slide, but I can't believe that this was the way that I solved it because it's really unnecessary. But I will walk through the mesh analysis just because I'm gonna eat crow. So the mesh, yeah, that's basically it. We basically did do nodal analysis. We just did KCL over here. But let me just step through the mesh analysis. So mesh number 1 is 4I1 plus 10 is equal to 0. In other words, we can immediately solve for I1 is 2.5 amps. Mesh 2 is negative 10, because you have a voltage rise of 10 volts, plus 5 times I2 minus I3 is equal to 0. Now the value of Ix here is equal to mesh current I2 minus mesh current I3. And so we can substitute that in we can substitute Ix for I2 minus I3 here. And now we have a value for Ix, which was 2 amps, which we really could have gotten just by looking at this picture, right? You have 10 volts here, 0 volts here. So there has to be 10 divided by 5 equals 2 amps flowing here. Right. And so the value of IN is 6 amps. So this is one of those things where the first year I taught this course, I didn't see it. And that's when I made these slides. And so now I see it, that there's an easier solution. But definitely, if you don't see that, then mesh analysis will give you the same answer. And that's the wonderful thing about circuits is that as long as you apply the rules correctly, you will end up with the correct answer. One comment though, because this is something that sometimes you get into a situation where, or I get into a situation where the midterm question is solved by nodal analysis. And the student does a mesh analysis solution. And that puts the instructor in a really tough spot, especially if the solution is correct, right? So when you look at the midterm, and I haven't even thought about the midterm yet, it will be given probably sometime in early April. Make sure you read the question. If it says nodal analysis, do nodal analysis. If it says mesh analysis, do mesh analysis. If it says Thevenin equivalent, do Thevenin. If it says Norton equivalent, do Norton, because it's very difficult to know how to give partial points in those situations.
For this homework, the one that we had, does the same apply? Because some people use Kirchhoff rules. I didn't. Or can we just?
The homeworks are different. No. The homework. I mean, if the instructions are solved, you can solve any way you want. But I'm saying on questions where it says solve by mesh analysis, that's different, right? If we don't tell you how, you can do whatever you want, except for copy it from Course Hero or whatever else you guys use. Awful website. I'm turning into get off my lawn guy. Anyhow.
I have a question about the example from before.
Go ahead.
When
Previous slide?
Yeah, the previous example. When solving for Rn, how come the 4 ohms was not included?
That's a good question, right? Because remember when you're solving for their equivalent resistance, we disconnect the independent sources,
Mm-hmm.
right? And so we short circuit the 10 volt. So if you have a resistor in parallel with a short circuit, that
Oh, immediate.
resistor will not see anything.
Okay, yeah, that makes sense.
Okay,
Thank you.
you're welcome. All right, we are, oh, I didn't want to do that. Okay, use Norton's theorem to find Rn and In between terminals A and B, right? So the step one is to find the Norton resistance. And to do that, we disconnect the independent sources. And we have here we have a dependent source. So we cannot disconnect. We only disconnect the 10 amp independent current source. So that one we can disconnect. We can open circuit this branch. But this 2Vx battery has to stay in. Okay, and so this is our circuit with the independent sources turned off. And we need to apply a test voltage, or here we apply a test current. So you can choose whichever route you prefer. You can either apply a test voltage and measure the current, or you can apply a test current and measure the voltage. It's up to you. Here we apply a test current because we're going to be applying nodal analysis, but either way works, right? Go ahead, Omar.
Just a quick question. If you did use a test voltage, wouldn't that have just been equal to Vx at that point?
Yeah.
So wouldn't it have been a little easier to just do that?
Perhaps, perhaps it would have been. Yeah, this would have been, this would have been a volt. This would have been, that's actually a really good suggestion, man. That I think that's great. That's a really astute observation. This would have been a volt. This would have been 2 volts. So you would have had, so let's see. So this would have been, yeah, so what Omar just said is that instead we applied a test current here of 1 amp, and we're interested in finding V naught. Another solution would be, another approach would be to instead put in a voltage source here, a 1 volt test source, and measure the current flowing in. Both those ways gives you the RN. But what Omar said was that it would have been easier to put in a test voltage because then Vx would have been equal to that test voltage. And then we would have immediately known the value of Vx. Yes, test sources can be anything you want. It can be a million, it can be a gazillion, whatever you want. Because you just care about the ratio of the current, of the voltage to the current. So yeah, I think that's really interesting. And maybe what I'll do is I'll do it both ways. I'll just present this solution this way first. So here we have a mesh analysis problem where the value of I2 is equal to -1. So the KVL equation for this is 6I1 plus 2Vx plus 2 times I1 minus I2 is equal to 0. I2 is equal to -1. And Vx, which is the voltage drop from here to here, is equal to 2 times I1 minus I2. You substitute in 2I1 minus I2 for Vx. And then you substitute in -1 for I1, and you get that, sorry, -1 for I2, and you solve for I naught is equal to -0.5, which means, right, so if I1, which is the current down the 2 ohm resistor, sorry, I1 is mesh current 1, I2 is mesh current 2. I1 is equal to -0.5. I2 is equal to -1. So the current that flows down the 2 ohm resistor is equal to I1, mesh current I1 minus mesh current I2, which is equal to -0.5 minus -1, right? It's very tricky with the negative signs here. And so the net current flowing from here to here is equal to 0.5. So a resistance of 2 multiplied by a current of 0.5 is equal to 1 volt. And so our Norton voltage is equal to 1 volt divided by 1 amp is equal to 1 ohm. Now let's do it with the way that Omar suggested, because I do suspect that it will be easier. So what I'm going to do is I'm going to duplicate this. And I'm going to erase this for the time being. And I'm going to erase this. And this is going to be V0 is equal to 1 volt. Okay, so just this is a battery now, and maybe I'll draw here. Oops. This is plus minus. Okay, right. So this is the situation we're dealing with. So I haven't done this before. I hope it works out. We have this is now equal to 1 volt. This is equal to 2 volts. And so let's see.
Would the voltage from the 6 ohm resistor be -1 then?
Well, yeah, this node will be grounded, right? So this is sitting at 0 volts. And then you go -1, -3, I believe. This is -3 volts. So the current here is equal to -0.5 amp. Or no, sorry, not negative. Positive. Right? This is 0 minus -3/6. So this is 0.5 amp. So 0.5 amp is flowing here. Let's see. Now the question is, what is the current? Yeah, the problem is we don't, that 0.5 amp, I think, has to also flow down. I think the current is confined to this mesh here. The question is why, there's no way of knowing what the current is through the battery, unfortunately. And maybe that's why the test current was applied and not the test voltage, because in this picture, it is not, if you wanted to do a KCL equation at that point, it's not possible because we have no way, like this is sitting at 1 volt and this is sitting at 1 volt. And so there's no voltage difference here, but there's also no resistance. And so you have a 0 divided by 0, right? The current from here to here is undetermined because V0 is equal to 1 volt. So these 2 points are all at 1 volt, but there's also no resistance between them. So unfortunately, I don't think that this would actually, unless you assume that this 1/2, if you assume that this 0.5 amp ends up flowing down the 2 ohm resistor, then you're set. Then you know that V0 is equal to 1. And you know that I0 has to, let's see. Yeah, no, you're still left with the same problem, which is that in this, we don't have any techniques in this course for determining how much current flows through a battery. Right? So there's no way of knowing, like we don't have any circuit rules for determining current here. Or wait a second, maybe we do. Let's apply, let's call this I naught. Let me actually erase all the, okay. Let's call this I naught. I just realized something. This is still ground. And I'm gonna actually, I'm just gonna label this because I think this is confusing. This is equal to 1. Okay. And this, I think we're fine. 2 volts. Right. 2Vx is equal to 2 volts because V naught is equal to Vx. So this point here, is equal to -3 volts. Okay. And so now go back to, so this current here is equal to 0 minus -3 over 6, which is equal to ½ an amp. And the current down here is equal to 1 volt divided by 2 ohms is equal to ½ an amp. Which, let me just see something. How did we get? In the previous, with the test current approach, we got that V naught is a volt, and we got 1 volt for 1 amp. And in our test voltage, we're plugging in a volt, but I must be doing something wrong because according to this, I now will be equal to 0, which does not make sense. So I must be doing something wrong. Yeah, you could do mesh analysis, but I'm sure the mesh analysis would, yeah, we can do. I mean, I don't really want to do it. I don't want to spend more time on this example. I'm just confused as to what is wrong here because this is 0. This, oh, hold on a second. This is a volt. Okay, this is what's wrong. This is 3 volts, not -3 volts. This is 0 volts. This is 1 volt. There's a drop from here to here of 2, which means this is 3 volts, which means that, okay, let's try this again. So this current here is this point is sitting at 0 volts. So this current here is 0 minus 3 over 6, which is equal to negative a half. Okay, so there's negative a half amperes flowing from left to right. And then there's half an ampere flowing down here. So the KCL equation I'll switch to text, would be negative 1/2 amps. I'll just draw it. Is equal to 1/2 plus I naught, which means that I naught is equal to 1 amp, which means that Rn is equal to 1 over 1 is equal to 1 ohm. So there we go. You do get the same answer. I guess the trickiest thing about this is deducing that the voltage at this point is 3 volts. And you get that by noting that this is ground. You go, there's a drop from here to here of 1, and there's a drop from here to here of 2. And so this point must be at 3. Okay. If there's any questions about what I've done so far with this problem, let me know. I will now go back to the slideshow because we're going to solve. So we have the solution for Rn, but we still need to know the value of In, right? So to get In, we're going to short circuit the Norton current. We're going to short circuit A and B. Okay, so this is what the picture looks like now. Right, so we've short circuited A and B, which means that this 2 ohm resistor is dead. It's not drawing any current because any current that makes its way here will bypass the 2 ohm resistor and take the short circuit from A to B. So here, one thing to note is that Vx is equal to 0, which means that 2Vx is equal to 0, right? So this is dead and this is dead. So all we have is a 10 amp current source in parallel with a 6 ohm battery and then a short on the right. So what I've done here is I've transformed the current source that's in parallel with a resistor to a voltage source in series with a resistor. And with that, you get that the Norton current is equal to 60 volts divided by 6 ohms. Looking at this again, I really didn't need to do this. I mean, this one way of seeing it, but another way, hopefully everybody sees that this becomes 0 and this can just be cut. So what we have in this circuit is the 6 ohm battery, the 10 amp current source, and the short, right? So in this configuration, the short circuit here will negate this, right? The 6 ohm resistor here will not draw any current because the 10 amp source has a 0 resistance path clockwise. And therefore IN is equal to 10 amps. So that's probably a more rational way of noting that all of this 10 amp current will take the outside path, right? Because Vx is 0, which makes 2Vx equal to 0. All right. Moving on, I'm going to wrap up the lecture. That's what I just did. So just a few words about maximum power transfer. So there are situations where you want to maximize the power that your device receives from a circuit. So the question is, how do you figure out, how do you design your circuit so that your load, which is another word for device, gets as much power, which is the product of voltage and current, as possible? So this is where the Thevenin equivalent or the Norton equivalent can be useful, right? So in other words, if this is A and B is like your wall outlet, and what's on the other side of the wall can be replaced with a Thevenin Thevenin equivalent circuit, which is a battery in series with a Thevenin resistance. And your device, RL, gets connected here. And this arrow here just means that the resistance of your device can change. You have a knob that you can turn that varies the resistance. So let's write an equation for the power that your device receives, right? So you know that the one equation for power is current squared times resistance. So let's figure out the current I in this picture, right? We can easily get it from Ohm's law, basically. The current I is equal to VTH divided by total resistance, which is RTH plus RL. Right? So what's inside the parentheses here is just a current that's flowing in the circuit. Another way of viewing it is what's inside the parentheses is equal to the current that your device draws from the wall. Square that and multiply it by your device's resistance, and you get an equation for the power that your device receives. And so why don't we tune the value of RL to maximize this quantity, right? And what you get, if you actually plot this function, and this is a good exercise for you guys, maybe in MATLAB or Python or by hand if you even want. If you sketch out the function P as a function of RL, what you'll see is that it exhibits a discrete maximum at the value of RTH. In other words, when your load resistance is exactly equal to the Thevenin resistance, the power that's delivered to your device is maximized. So in other words, your device's resistance should match the circuit's Thevenin resistance to get as much power into your device as possible. Another way of viewing this is for voltage division, the most voltage that this resistor can get is when the two resistances are equal to each other. And so when your load resistance is equal to RTH, you have maximum transfer of power. I've noticed a couple of people have already started to leave. That's all right. Perhaps they've heard from previous years that maximum power transfer never appears on an exam. Nah, I'm not. I was a student once, and you know, the good old days, if you fell asleep in the back of a lecture hall, there was no little sound to let the instructor know that somebody was tuning out. Homework 1 is due today at midnight Eastern Standard Time. If any of you are living in Hawaii, I'm sorry. I'm taking 6 hours away from you. What else? Send, for those 6 of you that have not sent your shipping information to Tariq, please do so immediately. I wish you guys all a good weekend and look forward to seeing you guys next Monday for day 10.
I have a question.
Oh, there we go.
So
Go ahead.
after our discussion on question question 6, I realized that I made a mistake. Can I just resubmit that part or do I need to resubmit everything?
Yeah, you're allowed to resubmit. So what I would do is just make a note on the PDF that you're submitting now. You're gonna submit. Just say that you're resubmitting only this question, and then the TAs can take your previous submission for the other questions.
Okay, thank you.
You're welcome. Thank you, you guys as well.